There's a star that shouldn't exist, not because it's too hot or too massive or in the wrong place, but because, according to our measurements, it's older than the universe itself. The universe, everything that exists, all of space and time, is 13.8 billion years old. We know this with remarkable precision. We can trace cosmic history back to the Big Bang, measure the expansion rate, analyze the cosmic microwave background radiation, and arrive at a number, 13.797 billion years, plus or minus about 20 million years. And yet, there's a star HD 140,283, nicknamed the Methuselah star, whose age we calculated to be 14.5 billion years old, older than the universe it exists within. A cosmic impossibility. You can't be older than your container. You can't have been born before time began. It's like finding a fossil that predates the formation of Earth, or a building constructed before the invention of architecture. It violates causality. It breaks the fundamental logic of existence. When astronomers first calculated Methuselah's age, they faced a crisis. Either our understanding of stellar evolution was wrong, or our measurement of the universe's age was wrong, or both were wrong, or something even stranger was happening. This is the story of that star, that paradox, and how scientists resolved it, not by discovering new physics, but by confronting the limits of measurement, the nature of uncertainty, and the humbling reality that even our most precise calculations come with error bars we can't eliminate. The Methuselah star didn't break physics, but it revealed something equally important, that the universe operates at scales of time so vast and processes so complex that measuring its age or the age of anything within it requires extraordinary care. And even then, we're working within margins of uncertainty. You're about to encounter a star nearly as old as time itself, born in the first billion years after the Big Bang, when the universe was young and strange and nothing like it is today. A star that has witnessed almost the entire history of cosmic evolution. A star that, for a brief moment, appeared to be impossible. Welcome to the paradox of the Methuselah star, the oldest thing we've ever found, and the scientific mystery that forced us to question everything we thought we knew about time. HD 140,283 sits about 190 light-years from Earth in the constellation Libra. By cosmic standards, that's practically next door close enough that we can study it in remarkable detail with modern telescopes. It's not a particularly impressive star at first glance. It's a subgiant, a star that has exhausted the hydrogen in its core and begun to expand and cool as it transitions toward the red giant phase of its life. It's about 80% as massive as our sun, shines with about 3.5 times the sun's luminosity, and glows with a pale orange-red color characteristic of old metal-poor stars. Metal-poor. That's the key detail. In astronomy, metals means anything heavier than helium. Hydrogen and helium were created in the Big Bang. Everything else carbon, oxygen, iron, gold, the elements that make up planets and people was forged in stars and scattered into space when those stars died. The first stars in the universe had no metals at all. They were born from clouds of pure hydrogen and helium left over from the Big Bang. When they exploded as supernova, they enriched the interstellar medium with the first heavy elements. The next generation of stars formed from gas that contained trace amounts of these metals. And with each generation, the metallicity of the universe increased. Methuselah has a metallicity about 250 times lower than the Sun. That means it formed from gas that had been enriched by only a few generations of stars. It's ancient. One of the oldest stars we've ever found. Scientists named it after Methuselah, the biblical patriarch who supposedly lived 969 years, the oldest human in the Bible. But the star's age makes that number look trivial. When astronomers first calculated Methuselah's age using stellar evolution models, comparing its luminosity, temperature, and composition to theoretical predictions of how stars age, they arrived at a shocking number, 16 billion years, plus or minus 2 billion years. That would make it older than the universe by more than 2 billion years. Even accounting for the uncertainty, the star's minimum age was 14 billion years, still older than the universe's 13.8 billion. There was no escaping the paradox. Something was wrong, but what? To understand why Methuselah's age was a problem, you need to understand how we know the universe is 13.8 billion years old. The universe is expanding. Every galaxy is moving away from every other galaxy, carried by the expansion of space itself. This was discovered in the 1920s by Edwin Hubble, who measured the velocities of distant galaxies and found that the farther away a galaxy is, the faster it's receding. If the universe is expanding now, it was smaller in the past. Run the clock backward, and eventually you reach a moment when all of space was compressed into an infinitesimally small point. That moment is the Big Bang, the beginning of space, time, matter, and energy. By measuring how fast the universe is expanding today, we can calculate how long ago the Big Bang occurred. This is called the Hubble time, and it gives us a rough estimate of the universe's age. But there's a complication. The expansion rate hasn't been constant. Gravity slows expansion by pulling matter together. And there's a mysterious force called dark energy that accelerates expansion by pushing space apart. The balance between these forces determines how the expansion rate has changed over time. To get a precise age, we need more than just the current expansion rate. We need to map the entire history of cosmic expansion. And the best tool for that is the cosmic microwave background. The cosmic microwave background, CMB for short, is the afterglow of the Big Bang. It's light that was released when the universe was 380,000 years old and has been traveling through space ever since, stretched and cooled by cosmic expansion. When we observe the CMB today, we're seeing the universe as it was in its infancy, a snapshot frozen in time. The CMB isn't perfectly uniform. It has tiny temperature fluctuations, hot spots and cold spots that differ by about 1 part in 100,000. These fluctuations are the seeds of structure, the quantum variations that eventually grew into galaxies and galaxy clusters. But the pattern of these fluctuations also encodes information about the universe's composition, geometry, and age. By analyzing the CMB in exquisite detail, we can determine how much ordinary matter, dark matter, and dark energy the universe contains. We can measure its curvature, and we can calculate how long it is bending. The most precise measurements come from the Planck satellite, a space telescope launched in 2009, specifically to map the CMB. After years of observations and analysis, Planck gave us a number, 13.797 billion years, plus or minus 0.023 billion years. That's the age of the universe. Not a guess, not a rough estimate, but a measurement with error bars of only about 20 million years, 0.17% uncertainty. It's one of the most precisely known numbers in all of cosmology. And Methuselah, according to initial calculations, was older. Dating a star is more complicated than dating the universe. With the universe, we can observe its entire history encoded in the cosmic microwave background. With a star, we only see it as it is now. We have to infer its age from its current properties and our understanding of stellar evolution. Here's how it works. Stars are born in clouds of gas and dust. When a region of a cloud becomes dense enough, gravity takes over, pulling the gas inward. As the gas compresses, it heats up. Eventually, the core becomes so hot and dense that hydrogen nuclei fuse into helium, releasing energy. Nuclear fusion ignites. A star is born. For most of its life, a star burns hydrogen in its core, maintaining a balance between gravitational collapse and radiation pressure pushing outward. This phase is called the main sequence, and it's where stars spend the majority of their lives. Our Sun is a main sequence star. So is Sirius, Proxima Centauri, and the vast majority of stars in the night sky. How long a star stays on the main sequence depends on its mass. Massive stars burn through their hydrogen quickly, often in just a few million years, because they need higher core temperatures to support themselves against gravity. Low-mass stars burn slowly and can remain on the main sequence for tens or even hundreds of billions of years. When a star exhausts the hydrogen in its core, it begins to change. The core contracts and heats up, igniting hydrogen in the shell around the core. The outer layers expand and cool. The star becomes a subgiant, then a red giant. Eventually, depending on its mass, it will shed its outer layers and leave behind a white dwarf, or explode as a supernova, or collapse into a neutron star or black hole. Each stage of stellar evolution is governed by well-understood physics. We can model how a star of a given mass and composition will evolve over time. We can predict its luminosity, temperature, and size at any age. To date a star, we measure its current properties, luminosity, temperature, composition, and compare them to stellar evolution models. We find the model track that matches the star's observed properties and read off the age. For Methuselah, the process went like this. Astronomers measured its brightness and distance to calculate its luminosity. They measured its spectrum to determine its temperature and metallicity. They plugged these numbers into stellar evolution models and found the track that fit best. The result, 14 to 16 billion years old, depending on the uncertainties in the model parameters. That's older than the universe. But here's the thing about stellar ages. They're only as good as the models. And models depend on assumptions about nuclear reaction rates, about how stars mix material between their cores and surfaces, about mass loss over time, about dozens of other factors. Small changes in these assumptions can shift the calculated age by billions of years. This is where uncertainty lives. When the scientific community realized that Methuselah appeared to be older than the universe, Reactions ranged from excitement to alarm. Some saw it as evidence that our cosmological models were wrong. Maybe the universe was older than we thought. Maybe the Hubble constant, the expansion rate, had been mismeasured. Maybe dark energy behaved differently in the early universe, changing the expansion history. Others suspected the stellar models. Maybe we didn't fully understand how low metallicity stars evolve. Maybe nuclear reaction rates at the extreme conditions in stellar cores weren't as well known as we thought. Maybe Methuselah had lost more mass over its lifetime than models predicted, making it appear older than it actually was. And some thought it might just be a statistical fluke that both measurements, universe age and star age, were at the unlucky ends of their uncertainty ranges, creating an apparent paradox that would disappear with better data. The paradox highlighted a fundamental tension in science. We had two independent measurements, both based on solid physics, both with quantified uncertainties that contradicted each other. When that happens, something has to give. Either the universe is older or the star is younger, or both numbers need adjustment. Astronomers went back to the data. They refined their measurements of Methuselah's distance using parallax, the apparent shift in the star's position as Earth orbits the Sun. Better distance measurements mean better luminosity estimates, which mean better age estimates. They improved measurements of the star's temperature and metallicity using high-resolution spectroscopy. They re-examined the stellar evolution models, tweaking parameters within physically reasonable ranges to see how much the age estimates shifted. And cosmologists reanalyzed the cosmic microwave background data, checking whether there was any way to push the universe's age older without violating other constraints. Slowly, the numbers began to converge. The refined distance measurement placed Methuselah slightly closer than previously thought, making it less luminous, which lowered its calculated age. Updated models of low metallicity stellar evolution suggested that earlier estimates had been too high, and the universe's age remained stubbornly fixed at 13.8 billion years. Every new cosmological measurement confirmed it. The latest calculations put Methuselah's age at 14.27 billion years, plus or minus 0.8 billion years. That uncertainty, range 0.8 billion years, is crucial. It means the star's age could be as low as 13.47 billion years, or as high as 15.07 billion years. The lower end is younger than the universe. The paradox statistically disappears, but the upper end still creates problems. If Methuselah is 15 billion years old, we're back to the impossibility. So which is it? Is the star younger than the universe or not? The answer is, we don't know for certain. The measurements overlap. Within their uncertainties, Methuselah's age and the universe's age are consistent, barely, just within the error bars. This is the nature of scientific measurement. We don't deal in certainties. We deal in probabilities, confidence intervals, margins of error, and sometimes those margins are wide enough that we can't definitively answer a question. Methuselah probably isn't older than the universe, but we can't rule it out completely. The resolution to the Methuselah paradox isn't a single dramatic discovery. It's the slow, patient work of refining measurements, improving models, and narrowing uncertainties. Modern telescopes like the Hubble Space Telescope and Gaia satellite have measured Methuselah's distance with unprecedented precision. Gaia, in particular, revolutionized stellar distance measurements by using parallax observations of over 1 billion stars. Better distances mean better luminosities, which mean better ages. Spectroscopic observations from ground-based observatories have refined measurements of the star's chemical composition. Knowing the exact amounts of oxygen, magnesium, iron, and other elements helps constrain stellar models more tightly. And theoretical astrophysicists have improved the models themselves. Better understanding of nuclear physics, better simulations of convection and mass loss, better accounting for how stars mix material internally, all of these refine the age calculations. Each improvement shrinks the uncertainty. The error bars get smaller. The measurements become more precise. And with each refinement, the paradox fades. The current best estimate places Methuselah's age at 14.27 plus or minus 0.8 billion years. The universe's age is 13.797 plus or minus 0.023 billion years. At the lower end of Methuselah's uncertainty, it's 13.47 billion years, safely younger than the universe. Most astronomers now believe that Methuselah is probably between 13.5 and 14 billion years old. Still ancient. Still one of the oldest stars we've ever found, but not older than the universe itself. The paradox is resolved not by discovering new physics, but by acknowledging the limits of measurement, by being honest about uncertainty, by understanding that when you're measuring objects billions of years old with processes that depend on dozens of interconnected physical parameters, your answers come with error bars you can't eliminate. This is science at its most mature, not claiming absolute certainty, but quantifying uncertainty and working relentlessly to reduce it. Methuselah taught us something valuable, that even our most sophisticated measurements are approximations, that error bars matter, and that when two measurements contradict, the solution often lies not in revolutionary new physics, but in patient refinement of the methods we already have. The star isn't older than the universe. It just appeared that way because we weren't measuring carefully enough. The Methuselah paradox teaches several profound lessons about science and our place in the cosmos. First, it demonstrates the power of error bars. Every measurement comes with uncertainty. Temperature, distance, luminosity, age, none of these are known exactly. They're estimates with margins of error, and those margins matter. When reporting scientific results, it's not enough to give a number. You have to give the uncertainty. You have to say 14.27 plus or minus 0.8 billion years, not just 14.27 billion years, because without the uncertainty, you can't compare measurements, can't resolve contradictions, can't make progress. Methuselah appeared older than the universe only when you ignored the error bars. When you included them, the paradox dissolved. Second, it reveals the limits of precision in cosmology. We can measure the universe's age to within 20 million years, about 0.17% uncertainty. That's extraordinarily precise for a 13.8 billion-year-old object. But when we try to date individual stars, especially ancient ones, our uncertainties are much larger, often 5 to 10% or more. This isn't a failure. It's a reflection of the fact that stellar ages depend on complex models with many assumptions, while the universe's age can be measured more directly from the cosmic microwave background. Third, the Methuselah star reminds us that the universe is old, profoundly, incomprehensibly old. Even if Methuselah is only 13.5 billion years old, that's 98% the age of the universe. It formed within the first few 100 million years after the Big Bang, when the cosmos was still young and strange. This star has witnessed almost the entire history of cosmic evolution. It was born when the first galaxies were forming, when the universe was smaller and denser and hotter. It has orbited the Milky Way's center hundreds of times. It has watched generations of massive stars live and die in supernova. It has seen our solar system form from a cloud of gas 4.6 billion years ago. And it's still here, still burning, still fusing helium in its core. In another few billion years, it will expand into a red giant, shed its outer layers, and leave behind a white dwarf, a stellar corpse that will cool slowly for trillions of years, outlasting every other star in the galaxy. Fourth, Methuselah shows us how science self-corrects. When the initial age measurements created a paradox, scientists didn't ignore it or explain it away. They investigated. They improved their measurements. They refined their models. They narrowed the uncertainties. And they resolved the paradox not by overturning cosmology, but by doing better science. This is how progress happens, not through revolutionary leaps, but through patient, incremental improvement. Measurement by measurement, model by model, paper by paper. Each refinement brings us closer to the truth. 190 light-years away, an ancient star burns. It's not impressive by cosmic standards, not particularly massive, not particularly bright, just a subgiant star in the constellation Libra, slowly exhausting its fuel as it transitions toward the end of its life. But that star is nearly as old as time itself. Methuselah formed when the universe was young, within the first billion years after the Big Bang. It condensed from a cloud of hydrogen and helium that had been enriched by only a few generations of stars. It ignited nuclear fusion and began its journey through cosmic time. For 13 to 14 billion years, it has burned. It has orbited the galactic center hundreds of times. It has watched the Milky Way grow from a collection of small proto-galaxies into the grand spiral we see today. It has witnessed the formation of our solar system, the emergence of life on Earth, the rise of consciousness. And for a brief moment in the early 21st century, it appeared to human astronomers to be older than the universe it inhabits. That paradox forced scientists to confront the limits of their knowledge, to question their measurements, to refine their models, to acknowledge uncertainty. And in doing so, they resolved the paradox not by discovering that the star was truly older than the universe, but by measuring more carefully, by narrowing the error bars, by being honest about what they could and couldn't know. Methuselah isn't older than the universe, but it's close. So close that it sits at the very edge of cosmic time, one of the oldest objects we've ever found, a witness to almost the entire history of existence. You live in a universe 13.8 billion years old. Methuselah has existed for 98% of that time. It's a relic from an era you can barely comprehend, from a time when galaxies were forming, when the cosmic microwave background was still glowing hot enough to see, when the universe was fundamentally different from what it is today. And somehow, that star is still there, still burning, still visible from Earth with a good telescope. A direct connection to the infant universe sitting in our cosmic backyard. Does it make you feel young? You should. Your species has existed for a few 100,000 years. Your civilization for a few thousand. You, personally, for a few decades. Methuselah has been burning for nearly 14 billion years. But here's the profound part. You can understand it. You can measure its age, infer its history, predict its future. You, a creature that lives for mere decades, can comprehend an object that has existed for billions of years. That's the miracle of science. Not that we know everything, but that we can know anything. That we can reach across billions of years with mathematics and observation and careful thought, and touch something as old as time itself. Methuselah is ancient, but you're the part of the universe capable of understanding just how ancient it is. And that matters more than you think.